The Arndt-Eistert synthesis is a series of chemical reactions that converts a carboxylic acid into the next higher homologue of that carboxylic acid. This process is known as homologation. In this reaction, diazomethane can insert a carbon between the carboxyl carbon and the adjacent carbon in order to make the chain one longer. In the first step of this mechanism, the OH group of the carboxylic acid is replaced by the chloride group in the presence of SOCl2, which forms the acid chloride. This step is completed in order to prime carboxylic acid for the nucleophilic attack. Next, the acid chloride will react with diazomethane to yield the formation of a diazoketone. The negatively charged carbon attacks the carbonyl carbon and the pi bond shifts up onto the oxygen, and then comes back down, which forces the chlorine to leave. The negatively charged chlorine ion will pick up a proton by attacking the hydrogen atom. The rearrangement of electrons and removal of HCl yields the formation of a diazoketone. Because this step occurs at high temperatures, the diazoketone is able to form several resonance structures. The next step in the reaction occurs via the Wolff rearrangement. The diazoketone will undergo hydrolysis in the presence of Ag+ and lose a nitrogen molecule. The carbene will undergo a 1,2 shift to produce a ketone. The ketone will be hydrolyzed, which will result in the formation of second carboxylic acid at a higher homologue. In this abbreviated reaction coordinate diagram, there are 4 transition states and 3 intermediate structures. The 3 intermediate structures are expected to be compounds 2, 4, and 6 from the previous mechanism. Overall, there is not a significant difference in the potential energy of the reactants and the products. A way in which you can speed up this reaction will be by increasing the temperature. IR isn't a powerful tool to determine the difference in the structure of the compounds for this particular reaction, since the starting material and final product both contain the same carboxylic acid functional group. In both carbon NMRs, there is a peak at about 180 parts per million, which accounts for the carboxylic acid functional group that is found in both compounds. However, there is an extra peak in the carbon NMR for the structure of the product. This extra peak, which falls around the range of 25 parts per million and is shown by the red arrow, accounts for the added carbon that occurs when the starting material is transformed into the next higher carboxylic acid homologue. The proton NMR of these structures reveals that the product has an additional 2H quartet to account for the 2 extra hydrogens that result from the elongated carbon chain. In a recent use of the Arndt-Eistert synthesis, the authors concluded that the use of certain reagents, such as amines or potassium carbonate, were ineffective in removing the hydrohalic acid and instead would yield the formation of ketones, which would hinder the diazoketone isolation. Thus, calcium oxide was determined to be the better choice for the hydrohalic acid scavenger in the Arndt-Eistert synthesis when compared with previous syntheses, which yielded the formation of less favorable aromatic and aliphatic diazoketones.